This is the Surface Impedance Measurement Apparatus, also known as SIMA. This is provided by McIntosh Applied Engineering, or MAE or MAE. When you get the SIMA device, the case comes with a photograph of what was originally in the case, so you can figure out if you've misplaced anything or what should have been in there. The control electronics has a sound card in it, and if that sound card needs its own drivers, the driver disk for that sound card will be included as well. This is the controller for doing the measurements. It has some custom data acquisition hardware in there, as well as the sound card. The controller needs a separate power supply, which is provided, and a USB connection to the computer through this USB cable. The case also has two measurement devices. This is the larger one. It's the MAE 130. It has a 1-inch diameter measurement area. This black disc here is where the acoustical impedance is actually measured at. This is good for low frequencies and higher intensity measurements. This is a smaller device. It's the MAE 131. It has a 12 millimeter measurement area. That black disc there is 12 millimeters in diameter. And this is probably going to be our preferred instrument to use. It has a wider frequency range than the larger 130 device. Each of the device has separate calibration volumes. Here's the calibration volume for the 130. These are the calibration volumes for the 131. We will take what we need out of here to do some measurements and show you some example measurements. So let's first take the controller out. We'll need the 131 and its calibration volumes. I'll leave the power supply USB cable in there. I've already got some out, and we won't use the 131 or the 130 for these measurements. I'll set this aside. Okay, so let's go ahead and power the controller up. And we need a USB connection to the computer. I'll plug that in. You should hear that enumerate once the USB is plugged in. I'll plug the 131 DB9 connector into the front panel of the control electronics, and I'll leave these out ready for the measurements. So now we'll go over to the Aries program, which controls all this, and start the measurement process. So here we are at the screen. I'll go ahead and run Aries. You can get Aries by contacting support at maellc.com. You'll be sent the software or a download link of where to get it. When you first run it, there's a little disclaimer you need to agree to use the software. And then you need to create a new module for doing surface impedance measurements. Aries is organized around different modules. There's several modules to do a variety of acoustic measurement and modeling activities, but we're going to do surface impedance for this time. So we'll go ahead and click there and create a surface impedance measurement module. First thing we need to do is we need to make sure that we tell Aries we're using a 131, and that is the case here. In the Setup tab, we see 131 is selected. We also need to make sure it's found the SIMA controller. So right here it's saying a SIMA controller has been found. So we're good to go. That's because we've plugged it into the USB already. And we want to enter an appropriate temperature for the air in the room that you're doing the measurements in. 77 is usually fine. Going back to the acquisition tab, there's two types of acquisitions that can be done: a device calibration and an impedance measurement. So we're going to start off by doing a device calibration of the 131. When we're done, we're going to get a new calibration curve, and these maximum sound card inputs will be updated as well. So I'm going to hit perform measurement. Aries will communicate with control electronics, and it asks us to place the 50 millimeter calibration volume on the 131 so we can proceed. So I want to go back to where the 131 is. And here's the 50 millimeter calibration volume. Here's the 131, so we're going to put them together and do a measurement. I've come to like to putty them in place. I've used rubber bands to hold them together before, but I think putty's kind of turned out to be my preferred technique here. It also ensures that I've got a good seal. Now when you hold these together, you need to make sure that both of them are mating properly, that the calibration volume isn't slightly off center there, and you've got a little extra gap between the calibration volume and the measurement device. So just be careful, putty it up, and it'll hold it in place, and we'll go back to Aries and do the first part of the calibration measurement. So back at Aries, we'll go ahead and hit OK because we've put the calibration volume on. Now this might take a minute or so. Aries is going to run a sine sweep to do the measurement. First time it usually has to run it a couple times to get all the levels adjusted correctly. So you should hear a slow swept sine. Takes about 10 seconds to run, and it'll run a couple times. There it goes with the second run. So it's happy with that, and now it's asking us to put the 5 millimeter calibration volume on. So we're going to go back here, take the 50 off, put the 5 on. And we'll go back to Aries and hit OK. This will do a higher frequency swept sine. And now it's done. So it's updated the calibration curve on the screen here, and it's updated the left and right maximum voltage into the sound card in the control electronics. When you calibrate a device, it's good to save the calibration data to a separate file so that you can have that later on. So we'll go to Files, Clipboard. Under Calibration Files, we'll hit the Save button, and I'm just going to type in MAE 131 here. It's good to put the date down so you know when you did the calibration. Also, as time goes on, it's nice to have a calibration history to see if the calibration has been changing over time. That might indicate that the calibration, that the device has become damaged at some point. When you get a calibration curve, it's good to compare it to the calibration curves that were published in the manual. To pull up the manual, you can go to the Help menu, select Surface Impedance Measurement Manual. The PDF document will come up, and we'll scroll down here and find the calibration section. And here's a calibration curve for the 131. And if you look, they roughly match each other. So it hasn't changed too much. So that's good. Now that we've got a calibration curve, we can go ahead and do a measurement. So under Acquisitions, we want to select the type of measurement to be impedance measurement. I'm actually going to measure a glass jar, a small 10-ounce glass jar. It has an opening area of 42 millimeters. I've already got these parameters set up. I'm going to do as wide a frequency range as we can handle here, from 20 hertz to 10 kilohertz. I'm going to change the dataset name to be just 10-ounce glass jar. When we do the measurement, it's going to create a dataset, and it's going to give it that name, so we'll know what we took. So I'm going to go back to the measurement area. I'm going to go ahead and take the calibration volume off the 131. And here's the glass jar I'm going to measure. It's just a 10-ounce fruit jar. And to put the 131 on the glass jar, I've got a aluminum plate. I put a 15 millimeter diameter hole in, And I'm going to putty the plate to the glass jar and putty the SIMA to the plate. So I'm going to look through there, try to get the SIMA device roughly centered in that 15 millimeter diameter hole. That's pretty good. I want to putty that plate onto that glass jar. Take some more putty, roll it out. Put along the lip of the jar. This is going to add a little bit of extra volume to the jar because I'm not going to squish that putty down completely. If you were doing a really sensitive measurement, you'd want to make sure the glass came in contact with the aluminum, but I'm not going to be that careful for this. So I'm going to squeeze the aluminum plate onto the jar, and we are good to go with a measurement of an empty jar. Head back to Aries. We've set up our parameters already, so I'm just going to hit Perform Measurement. You can hear the 131 do a sine sweep. Might take a couple times for it to get the levels adjusted to right. After it figures out the right levels, the other measurements will go quicker. So it had to run 2 times. It puts up a dialog box saying it's completed the measurement, and in this part of the measurement window we see the impedance that was measured. One of the things that stands out right away is we get some huge impedance spikes. This is due to the cavity modes of that glass jar. There's no damping in there, so these modes have an extremely high Q. Also, I always like to zoom in at the low frequencies and see what's going on down there. As you can tell, we've got the impedance at low frequencies is dominated by the imaginary part with this dashed line here, and it's going roughly to negative infinity, the imaginary part. So this is the classic impedance curve for a sealed volume. You can actually use this curve to compute what the actual volume is inside of the glass jar. So we'll auto scale back out. Next, I want to show you how you can control volume cavity resonances very simply by putting some damping material in. So I'm going to go back to the jar, and I'm going to take that plate off. And to dampen those modes, I've just got some simple felt here, just a piece of felt that I've cut up at odd angles. I'm going to stuff that in the jar. It's going to add some damping. I'm going to put the putty back on. I'm going to put the plate back on so we get it nice and sealed. So I've got a little bit of damping material in there. It's not full. It's probably about, maybe the volume is about 20% filled with felt, so it's not too full right now. We'll go back to Aries. I'm going to change the dataset name to glass jar with damping material. And I'm going to go ahead and hit Perform Measurement. So it takes a 10-second long swept sine. The levels have changed now because we don't have the extreme pressure ranges we got with those undamped modes, so it takes a couple times to do the measurement. So here we are. Here's the impedance. We see the negative 1 over j omega effect at low frequencies, indicating it's still behaving like a volume below about 500 hertz. And then we see these resonances again that are occurring at higher and higher frequencies. Here's the cavity resonances. This time they're heavily damped. They're still present, but they're not nearly as strong as when we didn't have any damping material in there. We can go to the plotting tab, plot both of those side by side, and it's actually kind of hard to even see the damped case because they're so small relative to those huge impedance spikes with the undamped cavity modes. So now we've done two measurements showing how a volume behaves with and without damping. We can discern a lot of information from this, but I want to show how this can be used with the modeler to predict how that how that volume would have affected the behavior of a speaker had that glass jar been used as a rear enclosure for a speaker. So to do that, we're going to want to import these impedance curves into the model. So before we go off and build the model, I'm going to go to the Files, Clipboard tab and export both of these. So I'm going to select the impedance, click Save. I'm going to save it to our directory, select the next impedance curve, hit Save, export that as well. Now I'm going to go and create a modeler module. So we're going to leave the Surface Impedance Measurement module behind and create a modeler module. I'm going to go ahead and create a speaker. I'll just use its default parameters. To model the impedance to the rear of the speaker as that volume, I'm going to need a resistance element. I'm going to need to terminate that resistance element with a pressure release element. So the impedance that we load in will essentially act as the series impedance for that element. So we ground it. So the impedance seen by the speaker is that impedance that we'll load in from the files we just exported. We want to drive the speaker with a voltage source. I need a reference ground on this. And I will put just a radiation element. We'll just keep the default values and not worry about all the details of this. To see the results, we're going to need a graph element. We'll connect it to the radiation element. Here's our model. And now we want to go ahead and import the impedance into this element here. To do that, you click on the element. Its parameters show up on the left pane of the modeler interface here, and we're going to select Load Impedance Data File. That'll bring up a dialog box, and I'm going to select the impedance that didn't have the damping at first. So I've got it in. To have it use it, I need to check Use Impedance Data, and then hit Calculate. And now when I go to my graph element, I can see here's the response of the speaker at about a foot away. I can see that there's some effects due to those modes. Now they're not very clear here because I'm doing a very coarse frequency analysis. If I go to the Global Parameters tab, I can change the frequency points from 200 to 2000. That'll give us a lot more resolution. I'll hit Calculate, go back to the graph, and now we can see the effect of those those cavity modes on the speaker quite a bit more. We get huge impedance spikes at some of those cavity modes, and that essentially brings the speaker diaphragm to a halt, and it has a large effect on the output. So we would not want to use an undamped volume for the back of a speaker. Let's go. I'm gonna save that in the graph element. I'm gonna save that curve to buffer A. I'm gonna call it glass jar without damping. Go ahead and plot it. And now I'm going to go back to this. I'm going to load the damped impedance curve in. I'm going to go ahead and hit Calculate. And now the graph is showing the impedance curve here in blue. Let me make those a little thicker here. Set buffer line, set to 2, set all, close. So our curves are a little thicker now. So in blue, we see the response with the damped impedance, and in green, the undamped impedance. Let me zoom in here. And the damping, you can still see some effect of the modes, but the effect has been reduced dramatically. You could probably live with the blue curve in terms of a speaker response, but there's no way you could live with the green curve in terms of the design. So this is an example of how you can use the SIMA devices to measure the impedance of a volume, use the modeler to apply it to a speaker model, and see what its impact is going to be. There's all sorts of other uses, though. The SIMA manual has a very good tutorial on how to do measurements with ports and how you can import that into the modeler and verify your measurements with some modeling elements and whatnot. But really, the sky's the limit with what you can do with this impedance device. There's lots of things that you can measure the impedance with. I think one of the key things is the SIMA device. When it measures the impedance, it lets you see the impedance of your acoustical structure, the acoustical device that you're designing. It's another way of seeing how it's actually behaving and be able to understand how different wall stiffnesses, different interior volumes affect the overall acoustic behavior of what you're trying to design. So I find it to be an extremely useful measurement tool, good for cell phones, tablets, designing headsets and whatnot. Thank you for your time. I hope you take some interest in it, and you're always welcome to contact May for further questions concerning any of these products. Thank you.